A planet larger than Earth may be hiding in our own solar system, not beyond another star, not in a distant galaxy, but in the cold darkness past Neptune. Its light is so faint that the greatest telescopes have struggled to find it, yet its gravity may already be written into the strange paths of icy worlds like Sedna. Somewhere out there, a silent super-Earth may be circling the Sun on an orbit so vast that 1 year could last thousands of Earth years. Welcome to Channel Name. Thank you for spending your time here and joining this quiet journey into one of astronomy's most mysterious searches. If this kind of deep space storytelling helps you relax, please leave a like, subscribe, and share the video with someone who enjoys cosmic mysteries. What time is it where you're watching, and from which place in the world? Leave a comment below. Now, let us drift outward, past Neptune, and begin the search for Planet 9. Far beyond the calm brightness of the inner solar system, beyond Mars with its red dust, beyond the giant planets and their rings, beyond even Neptune's dim blue path, the Sun becomes less like a blazing ruler and more like a remote star. Its light still reaches outward, but the warmth thins almost to nothing. The planets that dominate familiar maps fall behind, and the solar system opens into a colder, wider country, filled with fragments. They're dark, icy, and difficult to follow. Some are frozen remnants from the beginning of the solar system, preserved in a slow deep freeze for billions of years. They move through a region known as the Kuiper Belt, a broad realm of bodies left over from the age when the planets formed. From Earth, these objects are not grand sights. They do not glow with their own light. They borrow only a faint trace of sunlight, reflect a little of it back across immense distance, and appear in telescopes as tiny points that shift from night to night. Yet within those faint points lies one of the most persistent mysteries in modern planetary science. Some of them appear to move as though the outer solar system is not quite empty. The strange thing is not that these bodies have unusual orbits. The outer solar system is expected to be untidy, shaped by ancient scattering, distant tides, and the long reach of Neptune. Small icy worlds can be pulled, pushed, lifted, and stretched into paths that seem extravagant compared with the nearly flat orbits of the inner planets. Yet as more remote objects are found, a specific pattern begins to appear. A few of the most distant ones are not simply scattered at random. Their long orbits seem to point in related directions. Some lean at similar angles, some remain detached from Neptune, never coming close enough for the known giant planet to explain their present shapes. Others move on tilted paths that rise far above the common plane of the solar system. And a few even travel in directions that seem reversed compared with the orderly motion of the major planets. Individually, each orbit can look like a curiosity. Together, they begin to look like a clue. The clue is quiet because nothing in the darkness announces itself. No bright planet hangs obviously in the sky waiting to be named. No object sweeps through the telescope as Neptune once did when mathematics gave astronomers a place to look. Instead, the evidence appears indirectly, through the behavior of smaller bodies. This is the old language of gravity. A world does not need to be seen to leave a trace. It bends paths, rearranges timing, and creates families of motion where chance should create disorder. Jupiter disturbs great populations of asteroids. Neptune shapes the outer belt of icy bodies. The Sun holds all of it in a vast central grip. If another massive body exists far beyond Neptune, it too would not need to shine. It would only need to pull. Across millions and billions of years, even a weak pull, repeated again and again, can become a sculptor. It can turn randomness into alignment. It can lift orbits into strange inclinations. It can keep some bodies away from Neptune's reach and send others into paths that seem to have no easy origin. This is the basic reason Planet 9 enters the story. It is not introduced as a fantasy added to the solar system for drama. It appears as a possible solution to a pattern. Astronomers looking at the most distant known objects do not begin with a hidden world and then force the data to obey it. The puzzle begins with the objects themselves. Their orbits are measured, compared, and placed into models of the solar system. The question then becomes simple in form, even if difficult in practice. Can the known solar system make these paths on its own, or is something missing? The answer is still debated, and that debate is important. Observing the distant Kuiper belt is hard. Telescopes do not see every part of the sky with equal depth. Surveys often return to certain regions because of weather, telescope location, background stars, and the limits of observing time. A small sample can deceive. A pattern can look stronger than it really is if the search itself favours finding objects in particular places. This possibility, known as observational bias, remains one of the strongest cautions against claiming that a hidden planet must exist. Yet the pattern has not vanished easily. Several oddities remain suggestive enough to keep the search alive. The outer solar system seems to hold a structure that is difficult to dismiss, but also difficult to confirm. Planet 9, if it exists, is not expected to resemble Pluto. Pluto is a small, icy dwarf planet within the larger population of trans-Neptunian objects. The proposed Planet 9 would be far more massive, perhaps a super-Earth or a small ice giant. A type of world common around other stars yet absent from the known architecture of the solar system. It may travel on a huge elongated orbit, one that carries it hundreds of times farther from the Sun than Earth, and perhaps so far out that a single circuit takes many thousands of years. Such a planet would be cold, dim, and slow. It would not blaze across the sky. It would creep. In ordinary telescope images, it might look almost fixed unless the same region were checked again and again with great care. Its reflected sunlight would be extremely faint because sunlight has to make the long journey out, strike the planet, and then return across the dark. Distance punishes brightness twice. A world can be large enough to matter gravitationally and still be almost invisible to ordinary surveys. This is why the search feels both strange and plausible. The proposed planet may be moving through an enormous volume of space, along a path whose shape can be estimated but whose present location cannot yet be predicted with precision. The distant objects reveal something about the possible orbit, but they do not point to a single spot. The planet could be nearer and slightly brighter, farther and much darker, moving through a crowded star field or through a cleaner patch of sky. The search is not like looking for a missing coin on a table. It is more like trying to notice a nearly motionless ember across a continent of night. Still, the outer objects keep returning the same unsettling message. The solar system's edge may not be only debris, it may contain an unseen organizer. The word unseen matters because it places Planet 9 in the same tradition as some of astronomy's greatest discoveries. While also making it more uncertain, Neptune was predicted because Uranus did not move exactly as expected. In that case, the missing planet was close enough and bright enough that telescopes could confirm it once mathematics narrowed the search. Planet 9 is different. Its suspected influence is not on one known planet with a well-measured orbit, but on a sparse collection of faint bodies that are themselves difficult to track. The evidence is statistical, not direct. It is made from alignments, clusters, inclinations, and unlikely arrangements. That makes it both fragile and fascinating. If the pattern is real, it points toward a major discovery, a large planet hiding in the deep dark. A world missed not because it is small, but because space is vast and reflected light fades into almost nothing. If the pattern is not real, the lesson may be just as valuable. It would reveal how easily early maps of faint distant objects can mislead, and how carefully astronomy must separate structure from selection. Either outcome changes the understanding of the solar system's frontier, for now. The mystery remains suspended between evidence and absence. The Kuiper belt does not speak loudly. It offers only slow motion, faint light, and the patience of long orbits. A handful of distant worlds carry their paths like marks left in ice. Some marks may have been made by Neptune long ago. Some may have been shaped by passing stars in the sun's youth. Some may belong to a wider collective behaviour of small bodies acting together over immense time. But one explanation continues to draw attention because it is simple, powerful, and testable. Somewhere beyond Neptune, perhaps far beyond the reach of most past surveys, a planet may be circling in darkness. It does not need to announce itself. It only needs to leave the smaller world slightly out of place. In that quiet displacement, astronomers see the possibility of a ninth planet, not as a bright new dot already captured, but as a shape pressed into the motion of the distant solar system. The search begins with silence. And in that silence, the outermost fragments seem to remember the pull of something still unseen. The idea of a missing planet is older than the modern search itself. Long before the outer solar system becomes a place of computer models, infrared surveys, and faint icy worlds, the solar system is first understood through the slow wandering of lights in the night sky. Mercury, Venus, Mars, Jupiter, and Saturn are visible without instruments, and for ancient observers they stand apart from the fixed stars because they drift. They move against the background patterns as Earth and the other planets circle the sun in their own rhythms. For centuries, these wandering lights form the known planetary family. Their motions are watched and predicted, but they do not yet reveal the full size of the system. The solar system appears compact because human sight is limited. Beyond Saturn, there is no obvious bright signal. Uranus is there, but to the unaided eye it is too faint to behave like an unmistakable world. Neptune is deeper still, hidden not by mystery, but by distance and dimness. The first great change comes when telescopes widen the human eye. In the late 18th century, William Herschel studies the sky and notices an object that does not behave like an ordinary star. It shifts. Its small motion gives it away. The object is first mistaken for a comet, then understood as something far more important, a planet beyond Saturn. Uranus does not arrive as an expected completion of a model. It appears because a better instrument makes the sky more searchable. The known solar system doubles in width almost at once. A boundary that had seemed natural becomes temporary. This moment matters because it teaches astronomy a lesson that never disappears. The outer edge of the solar system is not where certainty ends. It is where detection becomes difficult. After Uranus, the next missing world is not found by simple looking. It is found through a disturbance. Astronomers calculate where Uranus should be, and the planet does not quite obey. Its orbit drifts away from prediction by a small but stubborn amount. The difference is not dramatic in the sky, but it is enough to trouble the mathematics. A planet is not supposed to ignore gravity. If the calculations are sound, then some force must be unaccounted for. Several possibilities can be considered, including errors in observation, inaccurate estimates of mass, or an incomplete understanding of the known planets. Yet one idea gathers strength. Another unseen planet may be pulling on Uranus from farther out. In the 19th century, Urbain Le Verrier and others turn the irregularity into a prediction. They do not merely guess that a planet may exist. They use gravity to narrow where it should be. When telescopes are aimed near the calculated position, Neptune is found. The discovery becomes one of the clearest demonstrations that invisible mass can reveal itself through visible motion. Neptune is not found because it is bright and obvious. It is found because Uranus carries the mark of its gravity. That success becomes a powerful memory in planetary science. It suggests that the solar system can be read like a set of tracks. When a known body moves oddly, the cause may be another body still hidden in darkness. This idea later feeds the search beyond Neptune, though the next chapter is more complicated. After Neptune is discovered, some astronomers believe that its own motion may contain unexplained traces. The calculations are uncertain, and the observations are not strong in the same clean way that Uranus once was. Still, the hope of another predicted planet grows. In the early 20th century, Percival Lowell and others search for what is sometimes called Planet X, an unknown world beyond Neptune. The effort is difficult, patient, and filled with expectation. Finally, in 1930, Clyde Tombaugh discovers a small moving object in images taken at Lowell Observatory. It is named Pluto, and for much of the 20th century it becomes the 9th planet. Yet Pluto is not the massive planet that Lowell had imagined. It is small, icy, and faint. Its discovery is real, but the old problem that inspired the search begins to dissolve as measurements improve. Neptune's supposed irregularities are not the strong evidence they first appeared to be. Pluto was found in the right broad region of the sky, but not because it truly caused the suspected pull. In that sense, the discovery is both triumphant and misleading. A new world enters the map. Yet the gravitational prediction behind it turns out to be weaker than the story suggests. Pluto's later history changes the solar system again. For decades it stands alone in the imagination, a tiny outpost at the edge of planetary order. It is strange compared with the other planets. Its orbit is more tilted and more elongated. It is small enough that its moon Charon is unusually large beside it. It seems less like the sibling of Neptune and more like something from a different population. That suspicion grows stronger when surveys begin finding other icy bodies beyond Neptune. The first of these new trans-Neptunian objects after Pluto appears in the late 20th century, and then more arrive. As telescope detectors improve and wide surveys become more effective, the darkness beyond Neptune fills with points. The Kuiper Belt becomes a real place in observation, not only a theoretical reservoir. Pluto is no longer alone. It is one member of a broad, icy family. Some objects are smaller, some are comparable, and a few challenge the old categories directly. The discovery of Eris, similar in size to Pluto, makes the question impossible to avoid. If Pluto is a planet, then perhaps many other icy worlds must be planets too. If the word planet is to remain a special category, then Pluto may need to be understood differently. In 2006, Pluto is reclassified as a dwarf planet. The decision is powerful for many people, but scientifically it reflects a changing map. The solar system does not become smaller when Pluto is reclassified. It becomes more complex. Instead of a neat sequence ending with a lonely 9th world, the outer system becomes a populated frontier, a place where small bodies preserve a record of ancient formation and later disturbance. The number of official planets returns to 8, but the idea of a possible 9th planet does not vanish. It simply changes form. The old Planet X searches had often been driven by suspected wobbles in the known planets. The new Planet 9 hypothesis grows from a different source, the orbits of many small bodies beyond Neptune. This shift is important. The mystery no longer depends on one planet moving slightly off course. It depends on whether a group of distant objects shares a pattern too orderly to be accidental. The history of missing worlds therefore becomes a history of better seeing. Uranus is found when telescopes improve. Neptune is found when mathematics follows a gravitational trace. Pluto is found in a search shaped by expectation, then reinterpreted as the first known member of a much larger belt. Each step expands the solar system and also corrects the previous picture. What once looks complete becomes provisional. What once looks lonely becomes part of a crowd. What once looks like a planet may later become a different kind of world. Planet 9 belongs to this same tradition, but with a modern caution that earlier generations did not always have. Astronomers know that patterns can mislead. They know that surveys have blind spots. They know that the outer solar system is not mapped evenly. They also know that history rewards careful attention to anomalies. Neptune's discovery shows that a hidden world can be found by the pull it leaves behind. Pluto's story warns that the desire for a missing planet can run ahead of the evidence. The present search holds both lessons at once. It looks outward with the memory of success and the discipline of doubt. At the edge of the solar system, the past does not offer a simple promise. It offers a rhythm. A boundary is drawn, then crossed. A planet is counted, then questioned. A faint point becomes a world, and later, a world becomes part of a wider population. The solar system is not a finished diagram handed down unchanged. It is a slowly revised map, built from small motions against the stars. If Planet 9 is eventually found, it will not restore an old order exactly. It will reveal a new architecture, one that has been present all along but hidden beyond the reach of earlier instruments. If it is not found, the search will still continue the same historical pattern, forcing astronomy to understand why the distant bodies move as they do. The missing worlds of the past show that darkness is not empty simply because it is uncharted. It is a place where the limits of seeing, measuring, and interpreting are tested again and again, until the solar system quietly becomes larger than it seemed. The strongest clues in the Planet 9 search are not bright images, but paths. They are arcs drawn so slowly through space that no human lifetime can watch them complete more than a small part of their journey. In the inner solar system, orbits seem orderly. Earth, Mars, Jupiter, and the other major planets move in the same general direction, close to the same broad plane, with paths that are circular beside the stretched roads of the distant frontier. The planets formed from a spinning disk of gas, dust, and ice around the young sun, and most bodies still preserve that old arrangement. Beyond Neptune, however, the order loosens. The sun is faint, the distances are vast, and small worlds remember collisions, close encounters, and ancient gravitational nudges. Their orbits can be tilted, elongated, and scattered into shapes that would look almost untethered if the sun were not still holding them. Yet the puzzle is not simple wildness. It is pattern inside the wildness. The first kind of strange orbit involves alignment. Some of the most distant trans-Neptunian objects have extremely stretched paths, carrying them close enough to be discovered for part of their orbit, and then outward into darkness for the rest. When astronomers map the directions of these long ellipses, a few appear to point in related ways instead of spreading around the sun at random. This is subtle. It does not mean that the objects sit together in space like stones in a pile. Each one is moving along its own huge orbit, and most are so distant that only a small portion of the path has ever been observed. The alignment is about the shape and orientation of the orbit itself, the direction in which each ellipse reaches farthest, and the way the orbit is turned in space. If chance alone were at work, these directions should blur into a scattered arrangement. Instead, the most remote objects seem to preserve a shared geometry. That shared geometry is what first makes the outer solar system feel less like debris and more like evidence. The second clue lies in inclination, the tilt of an orbit compared with the main plane of the planets. Distant icy bodies can lean sharply. A tilted orbit by itself is not shocking. Neptune can scatter small bodies, and the early solar system was not gentle. But several distant objects appear to share not only elongated orbits, but related tilts. A common tilt suggests that their paths may have been shaped by a persistent source rather than by isolated accidents. Gravity is patient. A massive body passing once can disturb an orbit, but a massive body remaining in the system can keep returning to the same work over immense spans of time. It can lift, rotate, and shepherd small objects until their paths settle into arrangements that look improbable without it. In the Planet 9 model, the hidden planet does not gather these distant worlds around itself. Instead, it tends to keep them away from its own path. The smaller bodies become arranged on the opposite side of the Sun from the planet, in a configuration that can remain stable, because the objects avoid close encounters. A third clue comes from detached objects. And here, the mystery deepens. Neptune is the outermost known giant planet, and its gravity dominates much of the region beyond it. When small icy worlds come close enough, Neptune can scatter them, changing their orbits and sometimes sending them much farther outward. Many trans-Neptunian objects can be explained through its influence, but some bodies, such as Sedna, follow paths that do not bring them close enough to Neptune for the known planet to have shaped them easily in the present solar system. Sedna moves on an enormous elongated orbit, with its closest approach still far beyond Neptune. It is detached because it remains outside Neptune's direct reach. That detachment is hard to explain. If Neptune did not place Sedna there, then something else must have lifted its closest point away from the giant planets. A passing star in the Sun's birth cluster could have tugged some bodies outward. The early solar system may have contained temporary planetary arrangements that later changed. The galaxy itself exerts a faint tide over great distances, yet a distant planet offers a continuing mechanism. Over millions of years, its gravity could raise the closest points of such objects, separating them from Neptune and leaving them stranded in a remote reservoir of unusual orbits. Then there are the high inclination and retrograde objects, among the strangest members of the distant population. Most bodies in the solar system travel around the Sun in the same direction, inherited from the original disk. Retrograde motion means an object orbits in the opposite direction. This does not require a planet to reverse it in one violent event. In some models, a distant massive perturber can slowly drive smaller bodies through a sequence of orbital changes, trading one property of the orbit for another until the path becomes steep, then nearly sideways. The process is slow and mathematical, but its result looks dramatic. Objects that once moved in ordinary paths can become lifted far above the planetary plane or turned into backward orbits. Before Planet 9 is included, these objects are difficult to place in a single coherent story. With a distant perturber, they become part of a wider pattern. The same unseen gravity that may align distant ellipses and detach objects from Neptune can also stir some bodies into extreme tilts. This is why the evidence for Planet 9 does not rest on one kind of anomaly. It is the combination that gives the idea strength. One strange object may be an accident, a few strange objects may be selection bias, but clustered orientations, detached bodies, high inclinations, retrograde orbits, and newly predicted populations of Neptune-crossing objects begin to form a more demanding puzzle. Each feature asks for an explanation, and the challenge is to explain them together without adding unnecessary invention. A single, distant planet is appealing because it can, in principle, act on all of these populations through one gravitational source. It does not make every detail simple, but it provides a common thread. A hidden planet can be massive enough to shape the outer system without being bright enough to have been easily found. It can be far enough away that its movement is slow and its sunlight nearly gone, yet close enough in gravitational terms to disturb icy remnants over the age of the solar system. Still, the pattern must be handled carefully. Distant objects are discovered only when they are bright enough and near enough for telescopes to catch. Many spend most of their orbits far beyond detection. Surveys are not evenly spread across the sky. And the Milky Way creates crowded fields where faint moving points become hard to separate from background stars. This means the observed population is not the true population. It is a filtered sample. If the filter is uneven, it may create the illusion of clustering. Astronomers arguing against Planet 9 often begin here, with the possibility that the strange arrangement reflects where surveys have looked, not where objects truly are. This caution is not a weakness in the search. A real planet must survive the removal of bias. Its predicted effects must remain visible as new surveys fill the gaps. The strange orbits therefore sit at the centre of a delicate balance. They are strong enough to suggest that the known solar system may be incomplete, but not yet strong enough to end the debate. They point toward a hidden mass, while also pointing toward the limits of the current map. They are not only clues about Planet 9, they are clues about how little of the distant solar system has been measured with certainty. Each new trans-Neptunian object can strengthen the pattern, weaken it, or change its shape entirely. A future population of hundreds or thousands of distant objects would transform the question from a fragile pattern into a statistical landscape. Then the alignments, tilts, detachments, and reversed motions could be judged with far greater force. For now, the distant bodies remain like scattered needles on a dark floor, each one pointing somewhere, not one of them alone enough to reveal the full design. Their orbits speak in fragments. Planet 9 may be the missing source of that record. A cold, massive world whose gravity has been writing itself into the paths of smaller bodies for billions of years. Or the pattern may fade as the census improves, revealing that the mind found order too quickly in a sparse and biased sample. The mystery remains powerful because both possibilities are scientific. The strange orbits do not prove a planet by themselves, but they keep the question alive, and they give the search its shape. In the silence beyond Neptune, motion becomes evidence, and the smallest worlds seem to carry the memory of something large. The Planet 9 model begins with an act of restraint. It does not begin by placing a world wherever imagination wants one to be. It begins by asking what kind of gravity could leave the distant solar system with the patterns already observed. The proposed planet is therefore not a bright character entering from outside the evidence, but a calculated absence, a mass inferred from the way smaller bodies seem to arrange themselves. In the model developed by Konstantin Batygin and Mike Brown, the missing world must be large enough to matter across enormous distance, but distant enough to remain unseen in the darkness beyond Neptune. It cannot be another Pluto, because Pluto is too small to organize the orbits of remote icy bodies on this scale. It cannot be an ordinary member of the Kuiper Belt, because the suggested gravitational reach is far greater than that of a small dwarf planet. The model points instead toward a world several times the mass of Earth. Perhaps a super-Earth, or a mini-Neptune, a class of planet that appears common around other stars but strangely absent from the known planets of the Sun. Astronomers have found many planets in the galaxy with sizes between Earth and Neptune, worlds too massive to be rocky twins of Earth in a simple sense, yet smaller than the ice giants. If Planet 9 exists, the solar system may contain its own example of this missing category, exiled to the edge, where it is seen only through its long gravitational shadow. The proposed orbit is as important as the proposed mass. Planet 9 is not expected to circle the Sun in the neat, nearly flat path followed by the familiar planets. Its orbit is thought to be elongated, carrying it closer to the Sun at one end and far outward at the other. It is also likely inclined, tilted away from the main planetary plane, as though the planet no longer fully belongs to the original disk from which the solar system formed. Such an orbit would make it slow, cold, and difficult to locate. A planet hundreds of times farther from the Sun than Earth receives only a ghost of sunlight. If it is near the distant part of its path, it moves even more slowly against the background stars, and it reflects so little light that even large telescopes must work near their limits. Yet in gravitational terms, slowness is not weakness. A body that remains in the solar system for billions of years can act repeatedly on smaller objects, reshaping their orbits not through sudden force, but through accumulated nudging. In this picture, Planet 9 is less like a wandering intruder and more like a distant metronome, setting a rhythm that only the most remote bodies are able to feel. The model explains the orbital clustering by placing the proposed planet on a path that is anti-aligned with the distant objects. This means that when Planet 9 is on one broad side of the Sun, the clustered icy bodies tend to stretch outward on the opposite side. The arrangement sounds strange at first, because it might seem natural for a planet to pull objects toward itself, but stable gravity often works through avoidance. If small bodies repeatedly came too close to a massive planet, they would be scattered, ejected, or thrown into new paths. Long-lived survivors are those whose orbits keep them away from the planet at dangerous times. Over many cycles, the configuration that persists is one in which the smaller objects remain organized but protected, held in a pattern that avoids direct disruption. The unseen world would not gather a visible cloud around it. It would carve a pattern into the empty spaces between orbits. The model also gives Planet 9 a role in producing detached objects. A distant body such as Sedna does not come close enough to Neptune for Neptune to easily lift it into its current orbit. In the Planet 9 framework, the hidden planet can gradually raise the closest points of such orbits, pulling them away from the reach of the known giant planets. The process is slow and subtle. A small icy world moves through its long path again and again, and each passage through the gravitational architecture of the outer system changes it slightly. Over time, its closest approach to the Sun can shift outward. It becomes detached, not because it has escaped the Sun, but because it has been separated from Neptune's strong influence. The same gravitational architecture can also help explain objects with high inclinations, or even retrograde motion. The hidden planet does not need to throw them violently backward. Instead, its repeated tugs can allow an orbit to exchange shape for tilt, becoming more stretched as it rises, or more tilted as its closest approach changes. The result is a population of objects that seem misplaced if Neptune is the only distant sculptor, yet become more understandable if another massive body is present farther out. This is where the model becomes more than a single explanation for a single clue. It becomes a framework. It tries to connect several odd populations under one cause, clustered distant ellipses, detached bodies, steeply inclined orbits, and objects moving against the usual direction of the solar system. A useful scientific model does not merely describe what is already known. It makes predictions that can be tested. Planet 9 models predict that additional distant bodies should be found in related orbital families. They also suggest that certain objects crossing Neptune's region may be continuously supplied from farther out, as if the outer solar system contains a slow river of icy bodies being disturbed inward. In a solar system without Planet 9, many such objects should either remain beyond Neptune's reach or be scattered away after encounters with the known giant planet. With Planet 9, the reservoir can be replenished. This gives astronomers a way to test the idea without seeing the planet directly. The small bodies become witnesses. Their numbers, paths, and tilts can either strengthen the model or expose its weakness. The estimated planet itself remains uncertain because the evidence is indirect. Its mass, size, brightness, and orbit are ranges rather than fixed facts. It may be several Earth masses, perhaps closer to the lower end of a mini-Neptune or higher than a typical rocky planet. Its atmosphere, if it has one, is unknown. At such distance, a gaseous envelope could be cold and dim, with internal heat leaking slowly into space. A bare, icy or rocky surface would reflect sunlight differently. A telescope does not look for mass directly. It looks for light, heat, and motion. If the planet is darker than expected, farther than expected, or hidden against a dense background of stars, it becomes harder to isolate. The model therefore narrows the mystery without solving it completely. It gives a broad road through the darkness, not a single doorstep. It says that if a planet is responsible for the observed patterns, it should have a certain kind of orbit and a certain kind of gravitational strength. It does not say exactly where the planet is at this moment. The distant icy bodies can help define the shape of the possible orbit, but they do not reveal where along that orbit the planet currently travels, because a full circuit may take many thousands of years. The planet's present position is only a tiny part of a huge path. It may be lingering near its farthest distance from the Sun, where orbital motion is slowest and brightness weakest. It may be closer, but still in a region not searched deeply enough. For this reason, Planet 9 exists in a curious scientific state. It is modelled with enough detail to be discussed as a possible world, yet not observed enough to be called real. It has a predicted mass, a possible orbit, and a set of gravitational effects, but no confirmed image. It is a planet in equations, simulations, and orbital statistics, not yet a planet in a telescope frame. That distinction keeps the language careful. The model may be elegant, but elegance is not proof. The patterns may be compelling, but patterns are not a discovery by themselves. Still, the model endures because it gathers many loose threads into one coherent shape. It explains why distant objects seem organized in ways that Neptune alone may not produce. It turns the outer solar system from a scattering of oddities into a possible architecture. If the planet exists, then the Sun's family is not simply a flat sequence of 8 known worlds with rubble beyond. It has a far outer member, cold and remote, moving on a long tilted ellipse, too dim for easy discovery yet massive enough to shape the darkness around it. In that model, Planet 9 is not merely another body added to a list. It is the missing weight that makes the edge of the solar system make sense. Sedna enters the Planet 9 story like a small red ember found far beyond the expected edge of Neptune's control. It is not large enough to command the architecture of the solar system, and it does not shine with anything like a planetary glow. It is a dwarf planet or near-dwarf planet, a frozen body coated in ancient reddish material, moving through a path so wide that most of its life is spent in darkness far from the Sun. Its discovery changes the mood of the outer solar system because its orbit is not merely distant, it is detached. At its closest approach, Sedna remains well beyond Neptune, too far away for the known giant planet to easily grab it, scatter it, or lift it into the strange path it follows now. That is the essential problem. Neptune is powerful in the region beyond its orbit. It can disturb icy bodies that wander near it, stretching their paths and throwing them outward. Many objects in the scattered disk can be explained this way. They pass close enough to Neptune that the planet's gravity becomes the clear source of their disorder. Sedna does not fit that simple pattern. It behaves like something that was once connected to the giant planets, then raised beyond their reach by a force that no longer appears in the ordinary map. Its orbit becomes a fossil of an event or influence that is difficult to see directly. The first question Sedna asks is not what it is made of, but who placed it there. A body cannot simply choose a distant closest approach. It must be moved. In the early solar system, icy leftovers formed in a crowded, unstable environment. The giant planets shifted, scattered material, and carved wide lanes through the disk that surrounded the young sun. Neptune's outward migration likely rearranged countless small bodies, populating the Kuiper belt and scattered disk. Yet pushing an object outward is different from detaching it. If Neptune sends a body into a long orbit, the body usually still returns close enough for Neptune to interfere again. The path remains tied to the planet that scattered it. Sedna's closest point stays too remote. It is as though the door back to Neptune has been quietly closed. Something has raised the near end of the orbit, turning a scattered object into an isolated one. This is why Sedna becomes more than a single curiosity. It suggests the existence of a detached realm, a population of bodies whose orbits begin beyond Neptune's strongest influence, and then stretch even farther into the outer dark. One detached object can be explained by an unusual past encounter. Several begin to suggest a mechanism. Other objects have since joined Sedna in this remote category, each with its own uncertain measurements, each carrying a similar message. The outer solar system contains bodies that are not easily produced by Neptune alone. Their paths are long, their nearest approaches are distant, and their histories seem to require a sculptor beyond the known planets. In the Planet 9 model, that sculptor is not violent in a simple sense. It does not need to strike these worlds or send them flying in one dramatic pass. Its effect is slow, repeated, and cumulative. A massive distant planet, moving on its own elongated and tilted orbit, can gradually change the closest points of smaller bodies. Over many cycles, it can pull some orbits away from Neptune, lifting them into a detached state. The image is not of chaos, but of quiet separation. A small icy world begins in a path that may once have carried it nearer the giant planets. Then, through the weak but persistent influence of a faraway mass, its orbit evolves. The closest approach drifts outward. Neptune's grip loosens. The body becomes stranded in a remote path, still bound to the sun, but no longer easily reachable by the known giant planets. This process matters because it explains why detached bodies can exist today without requiring every strange orbit to be made by a single ancient accident. The early sun was likely born in a stellar nursery, surrounded by other young stars. A passing star could have tugged on the outer debris, lifting some orbits and leaving Sedna like a surviving mark from that crowded beginning. This is a serious possibility, and it does not require a hidden planet still present. The trouble is that a passing star is brief. It can make a wound in the architecture, but it does not continue to organize the system afterward. Planet 9, if real, offers an active source that can keep shaping the detached population across billions of years. It could produce not only one Sedna-like orbit, but a continuing family of remote bodies with related behavior. The difference is between a scar and a living pressure. A stellar flyby belongs to the solar system's past. A hidden planet belongs to its present. Sedna also widens the scale of the search. Before its discovery, the region beyond Neptune could be imagined mainly as the Kuiper belt, with Pluto and its kin tracing a cold outer ring, and the scattered disk beyond it holding bodies flung outward by Neptune. Sedna points toward something more distant. Its orbit reaches so far away that it seems to approach the inner edge of the Oort cloud, the vast and mostly unseen reservoir of icy bodies thought to surround the sun at enormous distances. The Oort cloud is usually invoked to explain long-period comets, objects that fall inward from far beyond the planets after being disturbed by passing stars or the galaxy's tide. Sedna does not roam as far as the classic distant Oort cloud, but it is much more remote than the main Kuiper belt. It sits in a kind of boundary zone, a place where the inner planetary system, the distant comet reservoir, and possible hidden gravitational influences begin to overlap. That boundary zone is hard to map because its members are faint for almost all of their orbits. They become visible only when they happen to approach the Sun, and even then they are dim. Sedna was found near the closer part of its path. For the rest of its long journey, it would be vastly harder to detect. This means every known detached object is only the visible crest of a larger unseen population. Many others may exist, currently too far out or too faint for present surveys. The absence of many detections does not mean the population is small. It may mean that most of it is hiding where sunlight is almost gone. Each new survey adds a few more points to a map that is still mostly blank. The detached realm therefore becomes a test of patience. If Planet 9 exists, future observations should reveal more bodies with orbits that fit the pattern its gravity creates. If the detached population turns out to have a different arrangement, the model will need to bend or break. Sedna's value lies in that test. It does not prove a planet by itself, but it forces the question into sharper form. Something raised its orbit. Something placed it beyond Neptune's normal reach. The answer may be a hidden planet, a vanished stellar encounter, the combined gravity of an unseen belt, or a more complex early history of planetary migration. But the answer cannot be simple emptiness. Detached objects are reminders that the outer solar system is not just a leftover field of ice. It is a record of motion, memory, and influence. Their orbits preserve events too slow and too ancient to witness directly. In Sedna's path, astronomers read the possibility of a force still working in the dark, a distant planet that lifts smaller worlds away from Neptune and leaves them suspended in cold isolation. Or they read the echo of the Sun's birth environment, where nearby stars could have brushed the edges of the young system before drifting away forever. Both possibilities make the solar system less isolated and less finished than it once appeared. Sedna is small compared with planets, but its orbit has weight. It changes the question from whether objects exist beyond Neptune to how far the Sun's architecture truly extends. It asks whether the known planets are only the inner arrangement of a much larger design. Far from the familiar sequence of worlds, Sedna moves slowly, almost privately, along a road that takes it from dim cold to deeper cold and back again. It carries no answer bright enough to see at once. It carries a shape, and that shape keeps pointing toward a missing chapter in the solar system's history. In the search for Planet 9, the most important laboratory is not built from metal, glass, or mirrors. It exists inside calculations. The outer solar system is too large and too slow for direct experiment. No astronomer can wait for Sedna to complete its long journey, or for a distant icy body to reveal the full history of every gravitational nudge it has received. A single orbit can take thousands of years, and the most meaningful changes may unfold over billions. To understand such a place, and scientists build mathematical versions of it and let time run faster. These are simulations, numerical models in which the Sun, the known planets, a possible Planet 9, and swarms of small bodies are allowed to pull on one another under gravity. Each object follows the same physical rules that guide planets in the sky. A model can begin with a cloud of distant debris, then step forward again and again, calculating how every orbit changes as the ages pass. It can ask what the solar system should look like with an unseen planet, and what it should look like without one. If the known planets alone can produce the distant orbits, then Planet 9 may be unnecessary. If the strange patterns appear only when a massive outer body is included, the hidden planet becomes harder to dismiss. The challenge is that the simulation must not merely reproduce one attractive feature, it must explain several things at once. The distant objects appear clustered in the orientation of their long orbits. Some are detached from Neptune, others travel on steeply inclined paths, and some move in retrograde directions. These features occupy different parts of orbital behavior, so a weak model may solve one while failing another. A strong model must generate outcomes that resemble the observed frontier. Researchers begin with a broad set of possible Planet 9 properties. They vary the mass, the distance, the elongation of the orbit, and the tilt. They release many small objects into the model, often in arrangements inspired by what the early outer solar system may have looked like. Then they let gravity work. Over simulated time, most test particles do not survive in tidy ways. Some are scattered inward, some are thrown outward, some are ejected from the solar system entirely. Others settle into long-lived configurations, paths that could exist today. Those survivors matter most, because they are the ones a survey might find. In simulations with Planet 9, the surviving distant bodies often become organized in recognizable ways. Their elongated orbits can become anti-aligned with the planet, meaning they point broadly away from it across the Sun. The smaller bodies avoid close approaches that would destroy their stability. They survive because their paths keep them out of the hidden planet's most dangerous reach. Over time, the system filters itself. The objects whose orbits bring them into destructive encounters are removed. The ones left behind carry the pattern of the gravitational sculptor. The model does not simply pull objects into a line. It creates a stable architecture through the removal of unstable possibilities. Gravity does not only arrange what remains, it erases what cannot last. A second kind of fingerprint appears in the detached objects. In models without a distant planet, Neptune has difficulty producing and preserving remote orbits whose closest approach remains far beyond its reach. It can scatter bodies outward, but the same connection that lets Neptune scatter them often allows it to disturb them again later. With Planet 9 included, some bodies have their nearest points lifted away from Neptune. They become detached, stranded on long orbits that no longer return to the giant planet's immediate control. This behavior resembles the puzzle posed by Sedna and its relatives. The simulation does not prove that a real planet has done this, but it shows that a planet with the right properties can do it naturally. A third fingerprint lies in the most tilted objects. The model can drive some bodies into high inclination orbits by allowing their orbital shape and tilt to exchange over time. An object may become more eccentric, then more inclined, entering paths that rise far above the main planetary plane. In extreme cases, the orbit can flip into retrograde motion. The observed population is small, so these outcomes do not need to be common. What matters is that the model produces a supply of such bodies, and that their existence is connected to the same distant mass that explains the other patterns. A single hidden planet begins to act like a common cause behind several unrelated-looking mysteries. But simulations are not evidence by themselves. They are tools for making evidence meaningful. A model can be elegant and still wrong if the assumptions are poor or the observations are biased. Researchers therefore compare simulated populations to the way telescopes actually discover objects. Real surveys cover limited regions of the sky, reach limited faintness, operate during certain seasons, and avoid difficult backgrounds when possible. If a simulation produces a broad cloud of objects, but a telescope would only detect the few in one corner of that cloud, then the observed pattern may look more clustered than the real one. To test Planet 9 fairly, scientists must pass their simulated objects through the same selection effects that shape real observations. They ask not only what exists in the model, but what would be visible from Earth with specific surveys. This is where the debate becomes careful and technical. Supporters of Planet 9 argue that, after known biases are considered, the strange orbital patterns remain difficult to explain without the planet. Skeptics argue that the sample is still too small and too uneven to carry so much weight. Both sides are responding to the same difficulty: the outer solar system is only partly known. A few dozen extreme objects can suggest architecture, but a few dozen are also vulnerable to chance, bias, and hidden assumptions. Newer forms of modelling push beyond the original clustering question by making fresh predictions. One concerns objects that cross Neptune's orbit or move between the giant planets and the distant reservoir. If Planet 9 is present, its gravity may continually feed icy bodies inward from the far outer solar system. Neptune may then scatter many away, while Planet 9 keeps replenishing the supply. In this picture, the two planets act across distance like separate gates in a slow gravitational exchange. Without Planet 9, the number and distribution of such objects should be different. This gives the hypothesis a sharper edge. Instead of merely explaining the bodies already used to inspire it, the model points toward populations that can be searched for independently. If future surveys find the predicted supply in the predicted form, the hidden planet gains support. If they do not, the model loses ground. This is the strength of simulation when used well. It turns a mystery into a set of consequences. The digital solar systems can also test the age of the pattern. A true planetary architecture must survive for the age of the solar system, or at least for a large part of it. If a proposed orbit for Planet 9 destroys the distant population too quickly, it cannot be right. If it fails to keep the clustered objects stable, it cannot explain what is seen. The best models search for conditions that last through deep time, allowing the present outer solar system to emerge from a plausible past. They are not trying to create a temporary accident. They're trying to discover whether an unseen planet can maintain a long-lived structure at the edge of the Sun's domain. In that sense, simulations function like memory machines. They run backward and forward through possible histories, not to reveal exactly what happened, but to narrow what could have happened. They show which arrangements are fragile and which can endure. They show how a faint body, never directly imaged, might still be written into the orbits of distant ice. The phrase gravitational fingerprint is more than metaphor. A fingerprint is not the person, but it preserves contact. The strange orbits are not Planet 9, but they may preserve the contact of its gravity across immense time. Every clustered ellipse, every detached path, every steep orbit becomes part of a pattern that either belongs to a hidden world or exposes a deeper misunderstanding of the outer solar system. The simulations cannot decide the matter alone, because nature must supply the final data, yet they give the search its discipline. They prevent the idea from being only a story about a missing planet and make it a testable claim about motion, survival, and structure. In the dark beyond Neptune, there may be no visible glow from Planet 9, no clear disk in a telescope, no sudden announcement. But inside the simulated solar systems, its possible presence leaves order where disorder should dominate. Gravity leaves fingerprints, and the question now is whether the real sky carries the same marks. Far from the sun, a planet can become massive and invisible. This is the central difficulty in the search for Planet 9. The proposed world is not imagined as a tiny chip of ice, too small for telescopes to care about. It may be several times the mass of Earth, large enough to bend the paths of distant bodies and belong among the major architecture of the solar system. Yet size alone does not make a planet easy to see. A planet in the outer dark does not shine like a star. It reflects sunlight, and at an enormous distance that sunlight has already become thin before it reaches the planet. Then the reflected light must cross the same gulf again on its way back toward Earth. Each part of that journey weakens the signal. A world can be big enough to shape orbits for billions of years and still appear in an image as a faint point lost among background stars and galaxies. The problem is not only darkness, it is also the scale of the search. The sky looks like a dome from Earth. But for an object at the edge of the solar system, that dome becomes a vast field of possible hiding places. The orbits of distant trans-Neptunian objects can suggest the broad path Planet 9 might follow, but they do not reveal where the planet is along that path now. This is different from the discovery of Neptune, where calculations based on Uranus narrowed the search to a smaller region. In the Planet 9 case, the evidence comes from small distant bodies that have not been observed for complete orbits and will not be observed that way for many lifetimes. Their paths are inferred from short arcs measured over years or decades, then extended through gravitational models. These arcs help define the possible orbit of the hidden planet, but not its present position with precision. If the planet takes many thousands of years to circle the Sun, then a human observing record samples almost none of its motion. It could be near the part of its orbit where it is closer and brighter. It could be near the far end, where it lingers because orbital motion slows at great distance. That far end may be exactly where it is hardest to see. A second difficulty is motion itself. Planet 9, if real, would not sweep quickly across the sky. Nearby asteroids can betray themselves by moving noticeably between images taken on the same night. More distant Kuiper belt objects shift more slowly, but still enough that careful surveys can detect them over repeated observations. A planet hundreds of astronomical units away would creep. In some images, it might look almost fixed, blending with the background of stars. In others, its motion might be too small to catch without comparing observations separated by long intervals. But if the interval is too long, the sky itself changes in other ways. Variable stars brighten and dim. Galaxies and star fields create confusing patterns. Instrument noise, cosmic rays, image artifacts, and small detector flaws can mimic faint signals. A search must not only find a tiny moving point, it must prove that the point is real, moving at the right rate, and following a path consistent with a bound planet rather than some unrelated source. The background matters because the sky is crowded. Near the Milky Way, stars can fill images so densely that a dim solar system object hides among them. Away from the Milky Way, faint galaxies become common, and some may appear point-like. A planet would be visible only because it moves, but slow motion is easy to confuse with uncertainty. The telescope must see faint enough, cover wide enough, and return often enough. These requirements compete with one another. A deep exposure reveals dimmer objects, but it takes time. A wide survey covers more sky, but may not go deep enough. A repeated survey can detect motion, but it must spend years building the record. Earlier searches have been powerful, but each has had limits. Some looked deeply at selected regions. Some covered broad areas but could not reach the faintness required if the planet is far or dark. A non-detection can rule out certain possibilities, but it does not erase the entire idea. It may mean the planet is not in the searched region, not bright enough for that survey, or hidden in data never designed for exactly this purpose. The possible physical nature of the planet adds another layer of uncertainty. A mini Neptune with a thick atmosphere may reflect and emit light differently from a rocky super-Earth with an icy surface. Its colour, albedo, and internal heat determine how visible it is in different wavelengths. Albedo is the fraction of sunlight a surface reflects. A bright icy world is easier to see in visible light. A darker world absorbs more sunlight and returns less to telescopes. Yet at such distance, sunlight is already scarce, so even a reflective surface may be faint. Infrared observations offer another path, because planets can emit heat left from formation or slow internal cooling. But far infrared surveys have limits in resolution, sensitivity, and confusion with distant galaxies or dusty sources. A candidate signal must appear in the right place at the right time, move in a plausible way, and survive follow-up observations. One warm patch in old data is not enough. It must become a track, an orbit, and a physical body whose motion returns when telescopes look again. The planet's orbit also widens the uncertainty because it is likely eccentric and inclined. Eccentric means stretched away from a circle. Inclined means tilted relative to the plane where the known planets mostly travel. A tilted distant orbit can carry the planet through regions of sky not always emphasized by earlier surveys. The solar system is often pictured as a flat disk, and many searches naturally focus near that disk because many objects are expected there. But Planet 9 may not spend its life close to the familiar plane. If it is high above or below it from Earth's perspective, it can fall into areas where previous searches were thinner. It may also pass through parts of the sky that are difficult to observe from certain observatories. Earth-based telescopes are tied to latitude, weather, seasons, horizon limits, moonlight, and atmospheric conditions. The best search is a long campaign against geometry, faintness, and time. There is also the human problem of certainty. Astronomers do not announce a new planet because a faint dot looks interesting. The object must be seen more than once. Its motion must be measured well enough to calculate an orbit. The orbit must show that it is bound to the Sun and not a background source, artifact, or known body. The outer solar system has already produced false trails, promising hints that faded when better data arrived. Caution is not a lack of imagination. It is how a claim survives. This means Planet 9 might already exist in archived images without being recognized. It could be buried in a survey as one faint source among millions, too dim or too slow to pass the first filters used by automated software. Modern astronomy gathers more data than any person can inspect by eye. Algorithms search for patterns, link detections, reject noise, and classify moving objects. But algorithms are built with assumptions. A source that moves too slowly, appears only in one band, lies near confusion, or falls near the edge of a detector can be missed. Old data can become valuable again when new models suggest new ways to search them. This is why the hunt moves between past and future. Past surveys may already contain the planet as an unnoticed trace. Future surveys may provide the cadence and depth needed to connect that trace into a real orbit. The invisibility of Planet 9, then, is not magical. It is the ordinary consequence of a large object placed in an enormous, cold, poorly lit region, moving slowly through a sky filled with other faint things. The same distance that allows it to hide is the distance that gives it time to act gently on the outer solar system without disrupting everything at once. Its remoteness makes it hard to see and useful as an explanation. That tension defines the search. If it were close and bright, it would already have been found. If it were too far or too small, it might not shape the strange orbits at all. The proposed planet lives in the narrow middle, strong enough to matter and faint enough to evade. For now, the darkness beyond Neptune remains larger than the maps made from it. Somewhere in that darkness, a planet may be crossing a long tilted road, leaving almost no light but perhaps leaving order behind. To find it, astronomy must return, compare, measure, and wait for motion to separate a hidden world from the stars. Old data can sometimes behave like a sealed room. It sits quietly for decades, filed away after its first purpose seems complete, while newer instruments take over and the scientific frontier moves on. Then a question changes. A model sharpens, and the archive becomes alive again. In the search for Planet 9, this is exactly what happens with old infrared maps of the sky. The hidden planet, if it exists, may be impossible to catch by reflected sunlight alone, especially if it lies hundreds of astronomical units from the sun. But a planet is not only a mirror, it can also be a faint source of warmth. Even a cold world far from the sun can carry leftover heat from formation, heat trapped in its interior and released slowly into space over billions of years. This glow is not visible to human eyes. It belongs to the infrared, the part of light associated with heat. For a distant, dim, possible planet, infrared data offers a different kind of search. Instead of asking only where sunlight might reflect from a dark surface, astronomers can ask whether an object is radiating in the cold. The idea is delicate because the far infrared sky is crowded with confusing sources, dusty galaxies, star-forming regions, asteroids, clouds of interstellar dust, detector noise, and artifacts can all produce signals that look interesting at first. A true Planet 9 candidate must be more than a warm spot. It must appear as a point-like source, move by the right amount over time, fit plausible brightness expectations, and resist every ordinary explanation. This is why the old surveys matter. The Infrared Astronomical Satellite, known as IRAS, mapped the sky in the early 1980s from above Earth's warm, absorbing atmosphere. It was a landmark survey, opening the infrared sky with cold detectors that could see sources hidden from optical telescopes. More than 2 decades later, the Japanese Akari satellite made another infrared survey with improved capabilities. Taken separately, each survey is a map. Taken together, they become a time machine. They allow researchers to compare the far infrared sky across a span of 23 years and ask which sources have shifted. A distant solar system object should move against the background. It should not remain fixed like a galaxy. It should not flash randomly like noise. Its motion should be slow but real, consistent with an object bound to the sun at immense distance. The search through these archives is therefore less like looking at one photograph and more like matching 2 faint footprints in a snowfield after a long storm. Most marks are unrelated. Some are false. A few may align by chance. The task is to remove everything and keep only what still behaves like a possible world. In the reported infrared candidate search, researchers begin with millions of far infrared detections and then apply the expectations of the Planet 9 model. They consider a world in a broad mass range, moving on a distant elongated orbit, possibly lingering far from the sun where it would be slow and cold, because earlier optical and infrared searches have already constrained some nearer regions. Attention turns to distances farther out, where the planet could hide more easily. The expected movement across 2 decades becomes a filter. Too much motion would suggest a nearer object. Too little motion would suggest a background source. The right motion would fall into a narrow middle, where a planet hundreds of astronomical units away might drift just enough to be recognized. After many cuts, the huge field of detection shrinks dramatically. Most sources disappear from consideration because they're too bright, too extended, too fixed, too confused, too close to known objects, or inconsistent between the surveys. What remains is not proof, but a smaller set of questions. In the most intriguing case, a possible source appears in IRAS data, and a later possible counterpart appears in Akari data, shifted by an amount that could match the slow passage of a distant planet. The signal is faint, spread across only a small patch of pixels, and far from the kind of image that makes discovery feel immediate. It does not show a disk. It does not reveal clouds, rings, colour, or a surface. It is simply a possible moving infrared point, seen through the limits of old instruments. Yet context gives it force. If it is real, it could be the first trace of the hidden planet itself. The caution around that sentence is essential. Old infrared data is powerful, but it is also imperfect. IRAs and Akari were not built specifically to find Planet 9. Their beams are broad compared with optical survey images, and their detections can blend nearby sources together. The far infrared background is messy. A faint galaxy in one survey, a noise feature in another, or a patch of dust can masquerade as a moving object if the match is made too generously. The candidate's inferred path must also fit the orbit required by the outer solar system evidence. A source can move like something in the solar system and still fail to be the right source. If its inclination is too steep, its distance wrong, its brightness implausible, or its future position absent from follow-up observations, the candidate fades back into the noise of the archive. This is how astronomy protects itself from beautiful mistakes. It allows an exciting possibility to remain alive only as long as the measurements keep supporting it. Follow-up is therefore the true test. A real planet does not vanish when the archive ends. It continues to move. Its predicted position may be uncertain, but not meaningless. If the IRAS and Akari detections mark the same body, then later telescopes should be able to search along the possible track and either find another point or reduce the allowed space. Each new detection would tighten the orbit. 2 points separated by decades can suggest motion. 3 or more points can begin to define a path. With enough measurements, a candidate becomes an object. With an orbit, an object becomes a discovery. Without follow-up, it remains a possibility suspended between signal and coincidence. This is why the infrared clue is both dramatic and quiet. It may be a door, but it is not yet an opening. The archive also teaches something broader about the Planet 9 hunt. A hidden planet may not be found in the newest image first. It may be recognized by linking old and new records, by noticing that a faint source once dismissed or ignored has moved in just the way a distant world should. Modern astronomy is increasingly a science of memory. The sky is observed repeatedly in many wavelengths, and every survey leaves behind a frozen record of where things were at a given time. A planet with an orbit lasting thousands of years moves slowly enough that no single human era sees much of its journey. But the difference between observations taken decades apart can still matter. The past becomes a baseline. The longer the baseline, the easier it becomes to separate a solar system body from fixed background objects. Infrared archives provide one kind of baseline, and upcoming optical surveys provide another. If a candidate appears in old infrared maps, new optical data may either catch its reflected light or rule out much of the proposed track. If new optical surveys find a suspicious slow mover, old infrared maps can be checked for a warmer trace. The search becomes layered, with each wavelength testing a different aspect of the same unknown body. Visible light asks how much sunlight the planet reflects. Infrared light asks how much heat it emits. Motion asks whether it belongs to the solar system. Gravity asks whether it can explain the distant orbits. Only when these questions begin to agree does the hidden world become real. The possibility of an infrared candidate does not settle the Planet 9 debate, but it changes its texture. The mystery is no longer only a set of strange orbits waiting for a future telescope. It may also be an old signal waiting to be understood. A few dim pixels in archival data might be nothing more than noise, dust, or a distant galaxy. They might also be the first blurred trace of a planet so far from the sun that light barely returns. The difference between those possibilities is immense, and at present it rests on measurement, follow-up, and patience. In the cold outer dark, a large planet would not present itself as a grand image. It would begin as a discrepancy, a statistical pattern, a faint moving warmth, a point that refuses to stay fixed. The old infrared clues remind the search that discovery often arrives in fragments. The solar system may already have left its 9th planet in the records, hidden not beyond the reach of science, but inside data that needed the right question before it could speak. The search for Planet 9 changes when the sky is no longer treated as a collection of separate pictures, but as a moving record. For most of astronomical history, the outer solar system has been explored through fragments of time. A telescope looks at one region, then another. A survey covers part of the sky to a certain faintness. Years later, a different instrument returns with different filters, different depth, and different limits. From these scattered glimpses, astronomers try to find objects that move slowly, reflect almost no sunlight, and spend most of their lives near the edge of detectability. The Vera Rubin Observatory is built for a different kind of seeing. It does not merely look deeply, it looks deeply, widely, and repeatedly. That combination matters because Planet 9, if it exists, is not expected to reveal itself in a single dramatic image. It is expected to be faint, slow, and easy to confuse with a fixed background unless the same piece of sky is revisited again and again. Rubin's power lies in turning motion into evidence at an enormous scale. From its mountaintop site in Chile, the observatory is designed to survey the visible southern sky with an unusually large mirror and the largest digital camera ever built for astronomy. Each exposure covers a broad field, wide enough to gather huge areas of sky in a single look. Over time, these images become the legacy survey of space and time, a decade-long record of change, stars that vary in brightness, supernovae that flare in distant galaxies, asteroids that cross the inner solar system, and icy bodies beyond Neptune all become part of the same living map. For Planet 9, the important feature is not only depth, though depth is essential. The important feature is cadence, the repeated return. A distant planet may move so slowly that one observation cannot separate it from a faint star or galaxy. But across many visits, a solar system object should shift. Its motion may be tiny, but it should be coherent. It should follow a path, not flicker randomly. Rubin is built to create the kind of data in which such slow coherence can be found. The observatory also transforms the search by increasing the population of known small bodies. Planet 9 may be found directly as a moving point. But even before that happens, Rubin can test the gravitational case by discovering many more trans-Neptunian objects. The present debate is limited partly by sample size. The most distant and most useful objects are rare in existing surveys because they are faint, and because only certain regions of the sky have been searched deeply enough. Rubin can change the statistics. It may reveal hundreds or thousands of new icy bodies beyond Neptune, including objects on extreme, detached, tilted, and possibly Neptune-crossing paths. Each new orbit becomes another measurement of the outer solar system's structure. If the current clustering is real, the larger sample should strengthen it and sharpen its shape. If the clustering is a product of observational bias, the larger sample should loosen it, spreading the orbits into a more random pattern. In that sense, Rubin does not need to find Planet 9 immediately to become decisive. It can test whether the shadows that suggested the planet are truly there. A hidden world leaves a pattern. A survey that fills the gaps can show whether the pattern survives. Rubin's role is especially important because previous searches have often been forced to choose between depth and coverage. A very deep telescope image can see faint objects, but it usually covers a smaller patch of sky. A wide survey can cover huge areas, but may miss the dimmest bodies. Planet 9 requires both. It may be far enough away that only a deep survey can detect it, and its present location may be uncertain enough that only a wide survey has a realistic chance of covering the correct region. Rubin's speed reduces this conflict. It can gather broad images quickly, then return to them repeatedly. The result is not a perfect search of every possible hiding place, because no instrument is free from limits. Some regions remain crowded with stars. Some objects may be too faint, too dark, too far, or too close to the detection threshold. But Rubin dramatically expands the volume of possibility that can be tested. It turns the search from a hunt through selected patches into a systematic watch over much of the accessible sky. This matters for direct detection. If Planet 9 exists within Rubin's reach, it may appear as a faint source that shifts by a small amount between images. The discovery would not look like a glowing marble with visible weather and colour. It would begin as data a point at one time, a point at another, then another. Moving consistently, automated systems would link the detections. Astronomers would test whether the motion fits a distant solar system orbit. Follow-up observations would refine the path. The object would need to be checked against known bodies, artifacts, background galaxies, and false matches. Only when the motion survives would the candidate become serious. Even then, the first view would likely be humble, a dim spot whose importance comes from where it is and how it moves. A new planet can enter science not through spectacle, but through persistence. Rubin is also important because it may clarify the infrared clues. If a candidate from old far-infrared data has a plausible track, Rubin can search along that track for a faint optical counterpart, a planet that emitted enough heat to appear in old infrared surveys might also reflect a little sunlight, depending on its surface, atmosphere, distance, and size. A match between archival infrared detections and new optical motion would be powerful. A failure to find anything in the expected region would not always end the matter, because brightness predictions remain uncertain, but it would narrow the possibilities. The more Rubin observes, the less room remains for a hidden planet in the areas it can reach. This is how a great survey works. It does not only discover objects, it removes hiding places. The turning point is therefore not a single night. It is the gradual closing of uncertainty. Every repeated scan adds weight. Every new distant object improves the statistical map. Every non-detection in a well-searched region rules out a little more of the model. The Planet 9 hypothesis becomes more exposed to reality with each pass of the camera. This is why the observatory feels almost designed for the problem. Even though its scientific goals are much broader, it watches change, it builds baselines, it sees faint objects over wide fields. It gives astronomers the repeated images needed to separate distant motion from stillness. The outer solar system has always hidden behind three barriers: faintness, distance, and time. Rubin attacks all three at once. It reaches faintness with depth. It reaches distance by detecting objects that barely reflect sunlight. It reaches time by returning to the same sky so motion can accumulate into a measurable track. There is a quiet irony in this. Planet 9, if present, has been moving around the Sun for billions of years, shaping the outer system slowly enough that its influence becomes visible only through deep patience. Now the search answers with a machine built for patience at scale. The observatory does not stare at one suspected location and hope. It lets the sky unfold as a time-lapse, allowing slow bodies to separate themselves from the background. The possible planet and the survey are matched in slowness, one creeping through the darkness, the other returning with steady repetition. The outcome may be discovery. A faint moving point may appear, and the strange orbits may finally gain a source. It may be correction. Rubin may show that the clustering weakens when many more objects are known, dissolving the need for a hidden planet. It may be something more complex. revealing that the outer solar system contains structures not captured by the simplest versions of any current model. All of these outcomes are valuable because each replaces uncertainty with a more complete map. The search for Planet 9 is often described as the hunt for a missing world, but Rubin makes it also a census of the frontier. The observatory may find the planet, or it may explain why the planet was never needed. Either way, the darkness beyond Neptune becomes less abstract. It becomes populated, measured, and watched. At the edge of confirmation, the sky itself is becoming the experiment. The strange orbits have made their claim. The models have given that claim a shape. The old archives have offered possible whispers. Now Rubin begins the long act of listening with enough depth and repetition to decide whether the outer solar system is being held in order by a world still unseen. A strong mystery is not weakened by alternatives. It becomes sharper because every possible answer must survive the same evidence. Planet 9 remains compelling because it gathers several strange features of the outer solar system into one gravitational story. But a compelling model is not the same as a confirmed world. The darkness beyond Neptune may be hiding a planet, or it may be hiding a flaw in the way the evidence has been collected. It may hold a different structure, a past disturbance, a small compact object, or even a hint that familiar gravity behaves differently in the weakest reaches of the Sun's domain. Each possibility carries its own difficulty. Each must explain why certain distant bodies appear clustered, why some are detached from Neptune, why some orbits are steeply tilted, and why a few objects seem to travel on paths that ordinary scattering does not easily produce. If Planet 9 is not there, the mystery does not disappear. It changes shape. The first and most conservative alternative is observational bias. This explanation does not require a new planet, a strange belt, a passing star, or a different law of gravity. It only requires the present map to be incomplete in a misleading way. The most distant trans-Neptunian objects are hard to discover. They are faint, slow, and visible only during the parts of their orbits when they come close enough to reflect detectable sunlight. Surveys do not cover the sky evenly. They avoid some crowded regions, revisit others more often, and reach different depths depending on telescope design, observing conditions, and background brightness. From this uneven search, a small sample can look organized even when the true population is not. If telescopes have mostly found objects in the places where they were most likely to look, then the apparent alignment may partly reflect the search pattern rather than the solar system itself. Bias is not an accusation against the observers. It is a natural consequence of looking for very faint things in a very large sky. The question is whether careful corrections remove the pattern or leave it standing. If future surveys find many new distant objects spread in all directions, the Planet 9 signal may fade into a lesson about selection effects. If the clustering persists after the map becomes much fuller, bias becomes harder to defend. A second alternative is that the distant bodies are not being arranged by one unseen planet, but by their own collective gravity. This idea treats the outer solar system less like a set of test particles waiting to be sculpted by a giant body, and more like a distributed system whose small members interact over immense time. A sufficiently massive distant belt could, in principle, create coherent patterns through many weak tugs rather than one dominant pull. In a distant belt model, the clustered elongated orbits may belong to a wider structure, an unseen population whose combined mass shapes the paths of its members. This would make Planet 9 unnecessary, but it demands something else enough material far beyond Neptune to matter gravitationally. That is not a small demand. The known Kuiper belt contains far less mass than such models often require, and if a massive distant belt exists, astronomers must explain why so much material remains unseen. Its bodies might be small, dark, widely spread, or simply too distant for earlier surveys. But the hidden mass cannot be invoked without cost. It solves the problem of one missing planet by replacing it with a missing population. Still, it is testable. A powerful survey should begin to reveal whether the outer solar system contains the numbers and arrangements such a belt requires. A third possibility reaches back into the Sun's youth. The solar system did not form in perfect isolation. The young Sun likely emerged within a cluster of other newborn stars. In a crowded environment where close stellar passages were more common than they are around the Sun today. A passing star could have tugged on the outer disk, lifting orbits, detaching bodies like Sedna, and leaving a fossil pattern that still survives. This idea has a natural appeal because it explains remote detached objects as scars from an early encounter. It does not require a large hidden planet to remain in the solar system today. The culprit may have passed by billions of years ago and vanished into the galaxy. The difficulty is persistence and detail. A stellar flyby is brief. It can disturb a population, but it does not keep acting. The present arrangement of distant orbits must therefore be a preserved ancient imprint rather than an actively maintained structure. That may be possible, especially for some detached objects, but it must explain the full range of orbital oddities with the correct shapes and orientations. The more the evidence appears dynamically organized in the present, the more a long-gone encounter has to work to explain it. Yet the solar system's earliest environment is uncertain enough that this option cannot be dismissed. The outer frontier may still carry a memory of another star that once passed close enough to bend the paths of ice. A more exotic alternative is that the unseen perturber is real, but not a planet. It could be a compact dark object with planetary mass, such as a primordial black hole. This idea sounds extreme because black holes are often associated with collapsed stars. But primordial black holes are hypothetical objects that may have formed in the dense early universe. If one had the mass required to disturb the outer solar system, it could be far smaller than a planet and almost impossible to see by reflected sunlight. Its gravity would act like the gravity of any object with the same mass at the same distance. So it could in principle shape orbits while remaining optically invisible. This option addresses one question. Directly, why has no bright planet been found? But it creates much larger questions. No primordial black hole has been confirmed. Capturing one into the solar system would be extraordinary. It might reveal itself only through subtle gravitational effects, rare interactions with passing material, or extremely faint radiation under unusual circumstances. As an explanation, it preserves the idea of a single distant perturber, but exchanges a hidden planet for an object from speculative cosmology. It is not impossible in the mathematical sense, yet it sits above the planetary explanation in complexity. A cold super-Earth in the outer solar system is strange. A captured primordial black hole would be stranger still. The last major alternative asks whether the problem lies not in the inventory of objects, but in the law used to calculate their motion. Modified gravity theories propose that Newtonian gravity, or its usual extensions, may behave differently in regimes of extremely weak acceleration. These ideas are often discussed in the context of galaxies, where stars at great distances from galactic centers move in ways that led to the concept of dark matter. Applied to the outer solar system, a modified gravity framework might create small extra effects that align or influence distant trans-Neptunian objects without requiring a hidden planet. This is a profound possibility, but also a difficult one. The solar system is one of the most precisely tested gravitational laboratories known. Any modification must preserve the successful predictions made for planets, spacecraft, moons, and countless smaller bodies, while producing just enough difference at the distant edge to explain the anomaly. That is a narrow path. For most astronomers, a new planet is less radical than a new gravitational law. Yet science keeps even radical options alive when data remain incomplete. These alternatives reveal why the Planet 9 question matters even if no planet is found. The mystery forces astronomy to examine its maps, its models, and its assumptions. Observational bias would teach caution about faint object surveys. A massive distant belt would reveal an unexpected reservoir of material beyond Neptune. A stellar encounter would connect the present solar system to the crowded environment of its birth. A compact dark object would open a startling link between planetary science and the early universe. Modified gravity would challenge the foundations beneath celestial mechanics. Planet 9 is the simplest dramatic answer, but not the only possible answer. The task now is not to choose the most interesting story, but to let the sky remove the wrong ones. New surveys will test the bias. New objects will test the clustering. Repeated measurements will test candidate tracks. The outer solar system may answer with a planet, or with the slow collapse of the planet hypothesis into something stranger or more ordinary. Either result deepens the map. If the missing world is not a world, then the strange orbits still remain, and they still ask why they are strange. At the edge of the sun's reach, absence is not emptiness. It is another kind of evidence, waiting to be separated from the dark. If Planet 9 exists, it is not only missing from telescopes, it is also missing from the story of how the solar system formed. The known planets carry a broad pattern that points back to a disk around the young sun. The inner planets are rocky because heat near the newborn star drives away much of the volatile ice and gas. Farther out, beyond the snowline where water and other compounds can freeze, larger cores gather enough material to become the giant planets. Jupiter and Saturn grow immense, while Uranus and Neptune become smaller ice giants beneath deep atmospheres. This arrangement is not perfectly simple, but it has a recognizable order. Planet 9, as proposed, does not easily fit into that order if it sits hundreds of astronomical units from the Sun. At such distances, the original planet-forming disk should be thin, slow, and unable to build a world several times Earth's mass in the available time. Material would be too spread out, collisions would happen too rarely. Growth would stall long before a large planet could emerge. A hidden world at the edge of the solar system therefore raises a second mystery beneath the first. Finding it would not only mean locating an unseen planet, it would mean explaining how a world large enough to matter came to occupy a place where ordinary planet formation struggles to create it. The leading answer begins closer to the Sun, in the crowded violence of the early giant planet region. In this picture, Planet 9 forms not in its present darkness, but among the growing cores of the outer planets. The young solar system may contain more large embryos than the surviving planets reveal. They compete for gas, ice, and orbital space. Some merge, some are swallowed into the giant planets, some are scattered. A body that begins as the core of an ice giant may grow to several Earth masses, but then suffer a close encounter with Jupiter, Saturn, Uranus, or Neptune before it can settle into a stable orbit. One powerful gravitational meeting can fling it outward, stretching its path into a long ellipse. If the encounter is too strong, the body escapes the Sun entirely and becomes a rogue planet, drifting between stars. If the encounter is strong but not final, the body remains bound, thrown far away yet still circling the Sun. Planet 9 may be such a survivor, an unfinished giant planet core that is neither part of the familiar planetary family nor fully lost to interstellar space. This ejection story has a quiet elegance because it uses a process already known to matter in planetary systems. Young planets do not form in calm isolation. They migrate through disks, disturb one another, and reshape their orbits before a stable arrangement emerges. Many planetary systems around other stars appear to have gone through violent rearrangements. The solar system looks orderly now, but its present calm may be the settled result of an earlier instability. If an extra ice giant core once existed, its absence is not surprising. The early solar system may have removed bodies that did not fit the final architecture. Planet 9, in this view, is not an outsider. It is a native planet, born in the same disk as the others, then exiled before the system finished arranging itself. It carries the chemistry of the giant planet region into a far colder orbit, preserving a record of the chaotic youth that the visible planets have mostly concealed. Yet scattering alone is not enough. A planet thrown outward by the giant planets usually either returns to cross their path again or escapes. To remain on a distant, stable orbit for billions of years, something must soften or lift the orbit after the initial scattering. One possibility is the young sun's birth cluster. The sun likely forms among many other stars before drifting into the quieter field it occupies today. In that crowded nursery, nearby stars exert weak but meaningful gravitational tugs. If a newly scattered planet moves far from the sun while the cluster is still present, the combined influence of passing stars and the cluster's gravitational environment can raise the closest point of its orbit. This process can detach the planet from the giant planets, preventing repeated close encounters that would otherwise eject it. The result is a body stranded on a wide, elongated, tilted orbit. It remains bound to the sun, but its path no longer brings it back into the dangerous inner region of the giant planets. In a sense, the same stellar neighborhood that may have disturbed distant icy bodies could also have saved Planet 9 from complete escape. Another possibility is that the gas disk itself helps. Before the sun's surrounding gas fully disperses, a scattered planetary core moving through leftover material could experience drag. Gas drag and disk interactions can damp orbital extremes, changing a wild path into one that remains distant but stable. This is difficult to arrange, because the timing and strength must be right. But the early solar system is not a static diagram. Gas, planetesimals, growing cores, and giant planets all interact at once. The final orbit could be the result of a sequence, not a single event. A close encounter may launch it outward, while leftover material and stellar tides help detach it. Its strange orbit would be a fossil of overlapping forces from the solar system's first unstable chapters. The captured planet idea tells a different story. In that version, Planet 9 does not form around the sun at all. It begins around another star, or perhaps as a free-floating rogue world after being ejected from its original system. During the sun's birth cluster phase, stars pass close enough for their outer planetary systems to overlap gravitationally. A planet loosely bound to one star, or wandering freely through the cluster, can be captured by another if the encounter removes just enough energy from its motion. Capture is difficult because a simple passing object usually enters and leaves, but in a crowded environment, with multiple stars, planets, and a cluster potential, capture becomes more plausible. The sun may have stolen a distant world from a sibling star before the cluster dispersed. If Planet 9 is captured, it is not a lost child of the solar system but an adopted one, carrying the composition and formation history of another planetary system into the sun's domain. Its chemistry might differ from expectations for a planet born near Uranus and Neptune, but capture also has difficulties. The captured world must end up on an orbit that explains the present distant objects without destabilizing the known planets. The encounter must be close enough to transfer the planet, but not so disruptive that it damages the young solar system beyond recognition. The probabilities are uncertain, and depend on the density and lifetime of the Sun's birth cluster. A captured Planet 9 is possible in broad terms, but it requires a particular history that can no longer be directly reconstructed. The scattered native planet usually feels simpler because it begins with material already known to have existed in the Sun's disk. But simplicity does not prove truth. The origin of Planet 9 may remain uncertain even after discovery. A telescope image would reveal position and brightness first, not birthplace. An orbit would help. If the planet's path is extremely inclined or unusually shaped, it might favour some histories over others. A rough size and brightness could hint at reflectivity. Infrared observations could estimate heat. Over time, measurements might reveal whether it resembles an ice giant core, a mini Neptune, or something more unusual. But such details would be hard to obtain across hundreds of astronomical units. Even confirmation may begin with only a faint point and a long orbit. This deeper mystery gives Planet 9 its full meaning. It is not simply a missing entry in a planetary list. It may be evidence that the early solar system once contained more large worlds than survived near the Sun. It may show that planets can be thrown outward and preserved as distant relics. Or it may reveal that the Sun once exchanged material with its stellar neighbours in a nursery that has long since dissolved. Either way, the planet would turn the solar system's edge into a memory of beginnings. A world now moving through cold darkness may have been born in a crowded disk, scattered by giants, steadied by passing stars, or captured during a brief encounter with another system. Its present silence would hide a restless past. The search for where it is therefore becomes inseparable from the search for where it came from. At the frontier, the hidden planet is not only a possible answer to strange orbits, it is a possible survivor from the solar system's most unsettled age, carrying the story of an origin that the known planets alone cannot fully tell. The search for Planet 9 now stands in a rare place in science, where an old mystery has become testable on a near horizon. For years, the hidden planet has existed as a shape made from absence. It is inferred from the stretched orbits of distant icy bodies, from the detached road of Sedna, from the strange tilts and reversed paths that seem to disturb the outer solar system's simple order. It is supported by models that show how a massive world, far beyond Neptune, could shepherd small objects into patterns that survive for billions of years. Yet it remains unconfirmed because no telescope has yet returned the necessary proof a moving point, seen again and again, following the cold arithmetic of a planet bound to the Sun. The edge of confirmation is therefore not a line already crossed. It is a narrowing region where evidence, doubt, and new surveys press toward a decision. What makes the moment different is that the search is no longer trapped only in speculation. The tools are catching up to the hypothesis. The Vera Rubin Observatory begins to turn the sky into a repeated record, not merely a set of isolated images. Infrared archives give astronomers old baselines that reach across decades. Larger samples of trans-Neptunian objects are expected to test whether the orbital clustering is real, or whether it dissolves as a product of how past surveys looked. The question is being forced out of the realm where several interpretations can comfortably coexist. A hidden planet cannot remain both necessary and invisible forever if the sky is searched deeply enough in the right way. Either its light, heat, and motion begin to align, or the space where it can hide becomes smaller and smaller until the model must change. This is the quiet drama of the present search. It is not only a hunt for a distant world. It is a confrontation between a pattern and the full sky. If Planet 9 is found, the first confirmation will probably look modest. It may be a faint point in a sequence of images, moving by just enough to separate itself from the stars. It may not seem impressive to the eye. The image may show no surface, no clouds, no rings, and no visible disk. Its importance will come from consistency. A detection in one image must connect to another. A candidate must move along a path that makes sense for a remote solar system body. Follow-up observations must recover it. The orbit must be measured well enough to show that it is not an artifact, not a background galaxy, not a known small body, not a random pairing of unrelated sources, but a large object following the Sun at immense distance. Only then does the faint point become a planet. In that moment, the solar system changes. The familiar list of major worlds no longer ends with Neptune. It extends outward into a far darker architecture, where a cold super-Earth or mini-Neptune has circled unseen throughout human history. Such a discovery would also make the strange orbits legible in a new way. Sedna and its distant relatives would no longer seem like isolated puzzles. Their paths would become part of a gravitational landscape shaped by a world that had been present all along. The clustered objects would become survivors of a stable pattern rather than statistical curiosities. The high inclination and retrograde bodies would become evidence of slow, dynamical lifting rather than scattered exceptions. A discovery would not answer every question, but it would give the outer solar system a missing centre of influence. It would also raise new mysteries immediately. The planet's size, brightness, temperature, atmosphere, composition, and origin would all become urgent. If it is a native planet scattered from the region of the giants, it would preserve a record of a more crowded early solar system. If it was captured from another star, it would be the Sun's most distant adopted world. If its orbit is more extreme than expected, the models would need revision even in success. Discovery would be an ending only to the question of existence. It would be the beginning of a much longer investigation into nature, history, and place. If Planet 9 is not found, the result is not empty. A careful absence would have meaning. If Rubin and other surveys map the distant solar system deeply, find many more extreme objects, correct the biases, and show that the clustering fades, then the Planet 9 hypothesis may give way to a better understanding of how early data can mislead. The outer solar system would still be strange, but the strangeness would be explained by the unevenness of discovery, the remnant effects of Neptune, ancient stellar encounters, or collective dynamics not yet fully measured. A non-detection strong enough to matter would not simply say that no ninth planet exists. It would say which kinds of planets cannot exist in which regions, with which brightness and motion. It would carve away possibilities and leave a more precise map of the frontier. In science, ruling something out is not failure when the test is strong. It is a way of replacing a compelling story with a truer one. The difficulty is that the answer may not arrive all at once. Planet 9 may not be found on the first pass of a new survey. Bias may not disappear after the first new objects. A candidate may appear, then linger in uncertainty while follow-up tries to recover it. The orbit may remain too poorly known for months or years of observations. Old infrared clues may point toward regions that are searched without immediate success. New trans-Neptunian objects may strengthen one part of the model while weakening another. The edge of confirmation can be uneven, more like dawn than a switch. The sky brightens gradually with data. Each new object, each non-detection, each candidate, each refined simulation changes the balance. The mystery becomes less a single question and more a tightening net. Planet 9 either appears inside that net, or the net closes around the reasons it once seemed necessary. This slow narrowing is fitting because the possible planet itself belongs to slowness. Its orbit may take many thousands of years. Since the rise of the first civilizations, it would have moved through only a small part of its path. Since the invention of the telescope, it would have barely shifted in its long seasonal arc around the Sun. The solar system may have carried this world in darkness through all of recorded history, while human maps change from wandering lights to 8 planets, from Pluto's lonely edge to a crowded Kuiper belt, from photographic plates to digital sky surveys. Planet 9, if real, is not new. Only the search is new enough to notice it. That thought gives the mystery its calm force. The planet does not need human discovery to exist. An absence from a catalogue is not absence from nature. The outer solar system has always been larger than the portion already named. At the same time, the possibility of being wrong remains part of the wonder. The same evidence that points toward a hidden planet may instead reveal a deeper lesson about perception. The mind is drawn to patterns, and astronomy must ask whether the pattern belongs to the sky or to the method of looking. The strongest science does not protect a beautiful hypothesis from correction. It exposes it to better instruments. Planet 9 is now being exposed. The distant bodies have made their case in the language of motion. The simulations have answered with possible histories. The archives have offered faint hints. The new surveys are beginning to ask the final questions with enough breadth and depth to matter. Somewhere in that process, the mystery will change. It may condense into a discovered world, cold and massive. Moving on a long-tilted orbit beyond Neptune, it may dissolve into Bias, ancient disturbance, or another hidden structure. It may reveal an answer not yet fully imagined. What remains certain is that the search has already expanded the solar system in thought. It has made the edge less like a boundary and more like a region still under construction in the scientific mind. The known planets circle in their familiar order, but beyond them the small icy bodies continue along their long roads, carrying clues through darkness. Whether those clues point to a 9th planet or to a different truth, they are no longer silent. The solar system waits at the edge of confirmation, and the next map of its outskirts may be stranger, colder, and more complete than the last. Far beyond Neptune, the search settles into a quieter form. The distant bodies keep moving through their immense orbits, slow enough that their paths seem almost still, yet steady enough to preserve the memory of gravity. Each faint object holds a small part of the pattern. Each survey adds another point to the map. The question of Planet 9 remains open, but it no longer feels like a rumour at the edge of astronomy. It feels like a careful experiment unfolding across darkness, patience, and time. If a hidden world is there, it has already spent billions of years circling the sun in silence, receiving only a thin remnant of light, shaping small icy bodies without ever announcing itself. If it is not there, then the outer solar system is still speaking through some other structure, some old disturbance, some deeper arrangement not yet understood. In either case, the edge is not empty. It is active in the slow language of motion. The familiar planets continue their bright, ordered paths closer to the sun, while beyond them the frontier remains cold, wide, and unfinished. New telescopes now return to the sky again and again, allowing the faintest wanderers to separate themselves from the stars. The mystery does not need to be rushed. It belongs to long orbits, long records, and the gradual narrowing of uncertainty. Somewhere in the data, the answer may already be forming a dim point shifting against the background, or a pattern dissolving into something unexpected. The solar system remains what it has always been, larger than its maps, older than its names, and patient with its secrets. At its outer edge, darkness becomes a page still being read, and the possible 9th planet remains either a hidden world waiting to be found, or the shadow of a deeper truth still moving quietly beyond Neptune.